Hi humans, Anna Gray here. Today we are going to talk about finding the standard normal distribution in variable z. And as I mentioned in my previous video, I'm always going to start with the why. What are normal distributions and why do we standardize them? What is the point? So a normal distribution is a set of data that is symmetrical about the mean, thus creating a bell-shaped graph. So something that looks kind of along the lines, I'm not a good artist, something along the lines of this. Okay. And there are so many real world examples of normal distributions, which is why it's important to know. And some general ones, this over here, we've got IQ scores, heights of females, birth weights of babies, SAT scores, blood pressure. All of these are normally distributed variables, okay? Or normally distributed variables. So all of these would show on a bell graph. So in order for a distribution to be normal, the mean equals the median, which equals the mode, and the distribution must be symmetric about the mean, meaning that half the values have got to fall above and half the values have got to fall below the mean. So if we split this bell graph into two, that means that 50% are going to fall here and 50% are going to fall here. Okay, and that means that the total area under the curve is going to equal 100% or 1. So this total area is going to equal 100% or 1. Okay, so how does the normal distribution vary from the standard normal distribution? Why do we have to standardize the normal distribution? Well, a normal distribution is just a variation of the standard normal distribution. And what I mean by this is a normal distribution is just the standard that's either been moved to the right or to the left, or that has been shrunk or stretched. So in the standard normal distribution, mu, our mean, is equal to 0, and sigma is equal to 1. Okay, but a normal distribution has infinitely many variations, infinitely many mu's, infinitely many standard deviations, sigmas. So by standardizing the distribution, we can now compare different distributions with different means and standard deviations. And you can find the probability that certain values fall within your distribution, or that certain values or observations fall above or below a certain value. And so that is why we use z-scores. That is why we use the z-table. So let's take a look at an example of this, shall we? Let's get this up. Okay. Okay, so we are going to find the z-score that has 82.89% of the distribution's area to the right. So we know that this is a normal distribution, and we know that a normal distribution has a bell-shaped graph. So I always start with just drawing a bell-shaped graph. This helps you visualize a little bit better. I never extend the axis long enough on this side. I don't know why. Okay, so we know that we have two z's. Okay, we've got, because the bell-shaped graph is symmetric, so we have a negative and we have a positive z. Okay, and we are trying to find the z-score that tells us that 0.8289 or 82.89% of the area is to the right. So we know it can't be the z-score because we know that from here over is 50%. So this has got to be less than 50%. So the only accurate answer, the only answer that it could be, would be this. So we are trying to find this z. Okay, so we know that 82.89% of our area is from here above. So if we do 1 minus 0.8289, we get 0.1711, which tells us the area in this tail of our distribution. Okay, so we know now that the area of this tail holds 0.11% or 0.1711. Okay, so now we know the area above and we know the area below. And we know that the z-table uses the area below. Now we don't have a z-score. We are finding the z-score. So we are going to take our table and we are going to work not from the outside in, but from the inside out because we have the area. So we are trying to find the z-score that tells us the area below because that's how the z-table works. So we're not going to use the value 0.8289 because that's going to tell us the z-score with the area below it being 0.8289. But we need the z-score that's telling us the area below it is 0.1711. So we are going to look up that area in our z-table. It takes a little bit of searching. 1251, 1469, 1711. Look, it's exactly in here. If you don't have the exact number, you're going to find the value with the highest absolute value that is closest to the area that you found. So we found the exact number. So we're going to go from the outside or from the inside out, and we're going to find our z-score. So we're going to go to the left and we're going to find negative 0.9. And we're going to go up and we're going to find the camera 0.05. Okay, so we know that based on the table, our z-score is going to be negative 0.95. Okay, and we are going to check this by TI-84. By TI-84. So we're going to check this by calculator because you can also find this by calculator. So, got a calculator here. We're going to go to second, variables. We're going to go down to number 3, which is invert norm. And invert norm, again, we're going to use to tell us the area below our z-score. So we're going to put in 0.1711. And we get negative 0.9498273216. Rounded to 2 decimal places is going to be negative 0.95. So we get z equals negative 9498273216, which rounded gives us negative 0.95. So we see the calculator answer and by hand, by z-table, both check out and are both equal to one another. Again, if there are any other examples of z-scores or standardizing the normal distribution that you would like to see, if you would like to see an example with the area to the left of the z-score, if you want to find the answer or you want to find an example being given the z-score and finding the area, please let me know in the comments below. And as always, I hope you all have a beautiful, wonderful week, and I look forward to seeing you next time. Again, keep me in the loop for what you're looking for. Thank you.